What's up, everybody? Today we're going to talk about something called Sylvester equation, and this equation has something to do with Lyapunov equation. For example, Lyapunov equation is a special form of Sylvester equation, and so I think that is appropriate for us to analyze it. And the theorem is the following. This, okay, let me get the color right. Yeah, this is known as Sylvester equation, and for given A and B matrices, and for any given for any given C matrix, X matrix is unique. We can find it and it's unique. Alright. And this situation only happens when A and B do not share any eigenvalue. Okay. So since we will repeat that many times in this video, don't worry about like getting it right for the first time, and let's move it on. And like again, not like formally, but a little bit more like mathematical expression can be stated here. For any C, there exists unique X such that Sylvester equation is satisfied. Holds true. And this happens if and only if there is spectrum, like spectrum of A intersection spectrum of B equals empty set. Right? Like it says in the theorem, A and B do not share any eigenvalue. Right? Okay. Let's continue. How this is an if and only if theorem. So how can we prove it? And we have condition 1, if and only if condition 2. Condition 1 implies condition 2, and then condition 2 implies condition 1. We will first look at this, and we will first look at this, I think. Yeah, alright. The equation, the Sylvester equation, is a linear system with m times n unknowns and the same number of equations. Hence, it is uniquely solvable for any given C matrix if and only if the homogeneous equation, this admits only the trivial solution. Okay, so whenever we have something like that, and A, let's say A is given, right? For any B or X to be unique, and there are some conditions. What are those? This matrix, this equation must only be satisfied by the trivial solution, right? Okay, because if there is any like non-trivial solution, let's say x0, we can always the x wouldn't be unique, right? Got it. Okay, let's move on. And all right, this is something that we like to prove. And okay, I'm having a problem with my, all right. Okay, this is something that we want to prove. Let us first prove this, right? And like condition 2 implies condition 1. Okay, we will try to prove that. And we just manipulated the first term, right? Nothing changed, and so we are looking at this, and this condition can also be written as this. However, for the cadence of this, like I think explanation, I will cover this like at the end of the video, right? Okay, so what you need to know is at this point, and assume if that is the case, that will be the case, right? Okay, just assume that, and I will cover it at the end of the video because it's not like a couple of lines of explanations. All right, so here we are looking at this, and since we have a to the k and b to the k, right, and for any k, like positive integer, we can like, for example, this is like an incredibly powerful statement, right? For example, 3a square x plus 2a, right? If that is correct for any positive, okay, this is not my best video, I guess. All right, we can also do the same in that side of the equation. So we can write 3. I mean, we can always like scale it, right? Okay, we can do that, and like in the same logic we can do that. So what do I mean by that? If we can do that for any k, if that's true, like we can construct polynomials, right? And we can use polynomials. Like if that's correct, but instead of writing that, we can write a more general statement, which is a polynomial of a and polynomial of b, right? Okay, because they are like the basis of polynomials, like general analytic polynomials. All right, I mean, okay, and okay, so what do I mean by that is we can consider any polynomials. However, since we have that type of advantage, let's consider characteristic equation polynomial of a, right? And all right, we can do that. We have the enough. I mean, it's okay for us to do that. And it's like by definition, this is 0, right? Like Cayley Hamilton theorem states that like every matrix satisfies its own like characteristic equation, right? And got it. So like eigenvalues are computed by looking at the or by solving the characteristic equation, right? Okay, so this is 0, right? We are investigating this relationship at the moment. If that's 0, and if that is the case, they don't have any like common eigenvalue, this will not be 0, right? This will not be 0. This may not sound obvious to you at the moment, but like characteristic polynomial, the solution of characteristic polynomial is eigenvalues of like in this case A matrix. And since the spectrum of A and spectrum of B have no common elements, and this will be like the eigenvalues of B, right? Imagine that, and we will not satisfy that, so it will not be 0. It will be something other than 0. And what and it means that this will not be 0, and x is 0. We know that, right? By like this is given in the condition. So we're just manipulating this term, right? And not equal to 0 means this term means that their spectrum don't match. I mean matrices of A and B. Okay, so we were able to prove condition 2 implies condition 1. Okay, so let's try to look at if condition 1 implies condition 2. Okay, let's focus on the second part of the problem. Yeah, let us first prove. Okay, this is condition 1 and this is condition 2. Okay, and yeah, I guess this will be the annoying part of the proof. So okay, here we are looking at this, right? And just to clarify that A implies B. We are looking at this, we are investigating that. And however, we can also like investigate equivalent version of it, which is not B implies not A. Okay, and this is called contrapositive. All right, and like let's call it A and let's call it B, right? And this is not B, not B, and this is not A, like just given in this, right, diagram. So we are here. Let's distribute that not operators. And okay, this is the effect of the not operator. And here, this part, okay, here this part is kind of smooth, and we are basically saying not A if and only if B, right? So we need to distribute that. So here we are looking at this, and let's explicitly expand that if and only if statement, and that's given here. All right, maybe I should better zoom. All right, that's great, I guess. And let's also expand this like implies operators, and they can be given as such. And then let's move on. Let's distribute the not operators, right? We have and because of the not we have or, and we have or, and then we have and then we have or and not A, B, not B, not B, B, A, not A. All right. So this is equivalent to that expression. All right. Let's call it A and let's call it B, and just substitute, right? Like given in this expression. So okay, this part is the same. All right, and we just substituted the given terms, right? And then let's also do some manipulations, or like for example clarify some parts. All right, so this not affects this equality, and this not operator affects this, right? Okay, maybe it might be hard for you to see that, but this not operator affects this like given in the rectangle, right? This expression. Okay, so try to look at the parentheses, right? And this not operator again affects this rectangle, right? And how does it affect? It affects this equality sign, right? So we are just investigating that, okay? And here we have a little detour, I guess, and like this expression, like data spectrum and kind of matching, that means, right? Because equality equals empty set means they don't match. However, inequal or not equal to empty set means it's not an empty set, so they have some common eigenvalues, right? And means that this expression means that A and B share an, I guess that was share an eigenvalue, and let us denote that with lambda. Okay, this is a typo. And we have matrix A and we have lambda, right? For every eigenvalue we have right eigenvector and then left eigenvector, right? And I guess this is right, and then this is left, and this is what we are familiar with most of the time. But if we are doing some type of like eigen decomposition, yeah, then we also care about left eigenvector. All right, we have matrix A, we have lambda, and we have right eigenvector associated with that lambda, and then we have left eigenvector associated with that lambda, right? And since this lambda is common, so we also have that lambda as an eigenvalue, and as a consequence of that, B also has U and B associated eigenvectors with that lambda, and as a result of that, by looking at the expression, right? By looking at the expression, is that and x can be written like this, right? So this is the expression, and here x we can substitute to given terms, and then by using the eigenvalue, right? You know, wait a sec. U, this is right eigenvector. Yeah. By using that, and yes, that should transpose. Okay, yeah. By using those expressions, we can obtain that, and this equals 0. So what we have is that x, we can obtain x as given like that, right? And this is not equal 0, so x is not 0. Here x is not 0. However, this expression is 0. So let me delete all of them because I wanna show you something. And let me get another color. Okay, this is what we have, right? And let's look at this. And this is what we were investigating. We assume, or we were investigating if that's correct, is that expression also correct, right? And since this is OR statement, and we are able to prove that if that's correct, that's correct. So we are kind of done. Therefore, we see that when their spectrum match, and we have that expression is true. All right. So we are done with the proof. I got it. It was, it was not like a completely clear explanation. However, I mean, this is the type of, proof that you need to do once in your life and then don't care about it at all, right? And so, yeah, look at the bright side. And let's talk about the appendix. And there were some manipulation that we didn't talk about, but it was like important and it was involved. So because I, and leave left that at the end of the video. So okay, what we were trying to do basically, okay, we just written this instead of this, right? We just have that type of manipulation, and the question is why, how, like ax equals xb, and how can we write a to the x, a to the k x equals x times b to the k for any positive integer, right? We can write how can we write that? It doesn't sound like intuitive at all, right? And so because of that, and we will, all right, to prove that, to show that it is something we can do, we will use something called like mathematical induction. And first we will have a base case, right? K equals 1. When k equals 1, we have this expression, and this is something that we know that's correct. So the equation holds true for the base case. Okay, this was step 1, right? This is base case. These are the type of things that you will do whenever you are, employing some type of inductive mathematical induction to prove something. All right. And in step 2, we have inductive hypothesis, right? Assume that we will have an hypothesis and we will look if, or investigate if that's correct. Assume that for some positive integer n, the equation here, that is the equation, holds true. We will assume that's true, all right? And by using that assumption, right, we will do some manipulations and check if the given assumption is correct. All right, it will be clear hopefully in a moment. So in step 3, we will what's called as inductive step, and we need to show that the equation holds for a equals n plus 1, right? Which means we need to prove this expression. All right, let me clear some of them. And we assume that this is correct, this holds true. And now we want to investigate what about this expression. All right, okay, so starting from the left hand side, this is the left hand side. Okay, we are looking at this, right? And we can write this term as like that, ax. And since we know that ax equals xb, right, this is something that we know from the beginning, we can just change that ax with xb, right? And by using, I guess, the associative property of matrices, and we can, express that expression like this, right? So, and here we will use our inductive hypothesis. What was it? We can write a to the n x, like we can write a to the n x as x times b to the n. All right, we written x b to the n, right? And here, by again using associative property of matrices, and what we have in the final stage, x b to the n plus 1. And you can see that's correct. Okay, thus we have shown that if the equation, this equation holds true, the equation, this expression with k's, also holds true for any positive integer k using mathematical induction. All right, so that's it, and we will use Sylvester equation for like Lyapunov equation related subjects, and hopefully more videos will be, we will cover more videos about LMI theorems and lemmas. And that's it for today, and thanks for watching.